Hello. 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 Let's see. We have a mic, yes. Oh, one of the curves, there's just way too much. It keeps it human.
You're so handsome. You're so handsome. Yes, you are.
Owl chapter, is the owl right in Canvas? Let's do next, chapter 4, part 2. Both of them are tonight? Okay, that makes sense. All right. All right, quiz questions. Here we go. Question 4. So nitrogen reacts with hydrogen to form NH3, which is ammonia, which burns. So this ammonia here that's produced in this reaction right here becomes, this product here becomes the reactant here. And then that's burned with oxygen to form nitrogen monoxide and 6 waters. Oh, then the nitrogen monoxide here, that's a product, becomes a reactant here. So let's see what we got. How many moles of nitrogen? We are way back to here. How many moles of nitrogen? This is what we're looking for. Moles of nitrogen. Will we have to start with to make 10 moles of nitrogen dioxide? So 10 moles here. How many moles of nitrogen monoxide would we have started with? The mole ratio is 2 to 2, right? 2 to 2. The 10 moles of nitrogen dioxide would be produced from 10 moles of nitrogen monoxide. This 10 moles of nitrogen monoxide that we start with here would have been produced here. The 10 moles of nitrogen monoxide that were produced here came from ammonia. And my mole ratio here is 4 to 4 or 1 to 1. So that would be 10 moles of NH3 that we started with. That 10 moles of NH3 was produced at the end of this reaction as a product. So how many moles of nitrogen would we have to start with? What's the mole ratio here? 1 to 2, correct? So if we started with 5 moles, run this in reverse, 5 would produce 10. This 10 here would produce 10. And that 10 here would produce 10. 12. 12 is kind of a long problem. It's exactly the same as page 7 of the learning guide. It is exactly the same as page 7 of the learning guide. This is the grams of water. If we take this grams of water and multiply it by 0.1119, that's the percent hydrogen. That's how many grams of hydrogen we have here. So this is 0.1444 grams of hydrogen. This 0.119 comes from this being 11, water is 11.19% hydrogen. .722 grams of carbon dioxide. Now our carbon dioxide, CO2, is 27.29%. So 0.2779. That gets us 1.312 grams of carbon. This carbon came from here, and this hydrogen here came from right here. So if we know 2 out of the 3, then we know our grams of oxygen is going to be 3.150 grams, which is the total, minus 1.312 grams for the carbon, minus 0.144 grams for the hydrogen. That gets our grams of oxygen to be 1.694. So now we have grams of everything. Convert those grams to moles, divide by the smallest to get empirical formula, right? Grams to moles, divide by the smallest to get empirical formula. Again, that matches up the example on page 7. Number 18. First thing we need in 18. Oh, we have a balanced equation. I'm going to write this out though. Yeah, I'm going to write this out right here. Let's figure out what we're looking for here first. 0.125 molarity here. 65.5 milliliters was reacted. The AgNO3 is 0.455 molarity and 25.0 milliliters was reacted. We're looking for grams right there, right? So we have a limiting problem. And this one actually works out kind of nice. We don't need our periodic table in the beginning here because we can quickly get how many moles. So if you deliver 65.5 milliliters of 0.125 molarity, how many moles is that? Well, we're going to start out with our single unit number. Change this to liters, 0.0655 liters of solution. And we're going to multiply that by 0.125 mole per liter. And that's going to get me moles. I don't, again, it's kind of nice. I don't need a periodic table. So my moles here is 0.00819. Liters times moles over liters. We're canceling out liters, right? How many moles of silver nitrate do we need? It's a 2-to-1 ratio. So we're going to multiply that by 2. We need 0.0164. I kept all my numbers in my calculator, so that's why I got that. So it's a 2-to-1 ratio. So the question is, how many moles of this do we have? Well, I'm gonna go up here. 0.0250 liters. Point 455 mole per liter of solution. Point 0.0114 moles. This is what I need. This is what I have. Do we have enough or too much? Do we have enough? No, right? We do not have enough. So the reaction is going to stop when what we have of this silver nitrate runs out of the AgNO3. So we're going to use what we have of this limiting to figure out our moles right here. And our mole ratio is, mole factor fraction here is 2 to 2, right? So we would produce 0.0114 moles, and we can for sure get that into grams. Okay, 20. So 20, our pH is 3.2. If that's our pH, what's our pOH? Our pOH would be 10.8, yes. Now, there's two ways to do this problem. There's two ways to calculate all of these. This is one way to do it. If my pOH is 10.8, my OH minus should be 10 to the negative pOH. In 22, the first thing we need is a balanced equation. So in 22, H2SO4, I'll write that first. I'm going to zoom in here now for 22. H2SO4 NaOH. Double replacement. Hydrogen takes place of sodium. This is a neutralization reaction. That would produce HOH or H2O, right? Hydrogen takes the place. This is +1 and -1. Water is really hydrogen hydroxide, right? H2O, hydrogen hydroxide. Now I should point out this, I can do it right up here. This is +1 for the hydrogen of the acid, sulfate -2. For sodium hydroxide, +1, -1 for the sodium hydroxide. So sodium takes the place of the hydrogen. So we need 2 sodiums. Now we got to balance this pig. Start with sodium. We have 2 sodiums here. We should put a 2 right here. Then what else do we need? We have 4 hydrogens. We would need to put a 2 right there. Okay, what is the concentration of H2SO4? We're looking for this molarity here. 10 milliliters of the solution. I'm going to convert this to liters right away. 10 milliliters. The molarity here is 0.20 molarity. And if I converted that 7.8 milliliters, point 0.0078 liters, 0.0078 liters. So here's what we've got. If I'm looking for a molarity, my final units need to be moles over liters, right? Moles over liters. I need to get moles over liters. I have my liters. How many moles is this? How many moles of sodium hydroxide reacted? Well, I can get that. This is nice. This problem, I don't need a periodic table. I have 0.0078 liters of solution. And my molarity is 0.2 moles per liter. So 0.00156 moles. For my sodium hydroxide, right? That's how much it took. Now we're saying that the 0.0078 liters of 0.2 molarity is 0.00156 moles. How many moles of H2SO4 is it going to take so that there's no limiting, everything turns into salt and water? How many moles of H2SO4 is it going to take? My ratio is 1/2, right? It's going to take half that for moles. 0.00078 moles. I need molarity. Doesn't have to look pretty. I'm going to draw my line. Divide that by 0.0100 liters, moles over liters, and I've got it. $25 is pretty much exactly the same. Except for its KOH. The last problem is exactly the same. It's going to take a 2 to balance it. And you set up 25 the same exact way as 22. It's the same. So we would end up with 2 HOH again. Oops. But this time it's going to be potassium sulfate. And the rest is exactly the same. So this quiz is what, tonight? Tonight, okay. All right, let's, chapter 4 is in the books. So chapter 5, we left off. We started talking about heat. Whether something is exothermic, we get heat out, or endothermic, we put heat into a reaction. And then we left off kind of on this chart on page 4. Now, this specific heat column is how much heat energy you have to add to raise the temperature of 1 gram of this substance 1 degree Celsius. Specific heat. When you go to OWL has references. Or reference in OWL, references, I think it's references, and I think it's General Chemistry 1. You click on that, it gives you a whole table of specific heats. Be sure to use that table that is provided in OWL for specific heats. Otherwise, they don't come out correct. The specific heat values are a little funky if you Google them. Some are a lot funky. Okay, then we said that if you have liquid water versus solid ice versus H2O as a gas or steam, it takes different amounts of energy to heat them up, depending upon what phase they are in. But it takes a tremendous amount of energy to heat up water. Look at 1 gram of water is way higher than anything. It takes a lot of heat energy to heat up water, which is nice because when it's 95 degrees outside in July, the lake doesn't turn to 95 degrees, right? It warms up some, but if it warmed up too much, all the fish would die from lack of oxygen. Okay, so we're going to do some specific heat problems here, a lot of problems. Okay. So specific heat, again, it's the energy required to raise the temperature of 1 gram of it 1 Celsius degree. The term specific means per gram. How do we calculate specific heat? Q, this is my heat energy in joules. It could be in calories. Doesn't have to be in joules. Could be in calories. Typically it's in joules, but you can do in calories, same thing. So we have the equation Q is equal to MC delta T. Energy, specific heat value, that's going to be given, unless you have to calculate it, and delta T, change in temperature. Okay, here's an example. How much heat is needed to warm 250 grams of water, about 1 cup, from 22 degrees Celsius, about room temperature, to near its boiling point, 98 degrees Celsius. And it tells us the specific heat. So we have Q is equal to MC delta T. I'm just going to put it in a line right there. I think we've got it all here. We've got 250 grams of water. Specific heat of water, 4.184 joules per gram degrees Celsius. My temperature change. I'll put it in as T final minus T initial. So we want this to end up at 98 degrees. Minus 22 degrees. Now, keep track of all your chickens, pigs, and cows here. We don't want anything down here that does not have units. Grams cancel out. My degrees Celsius are going to cancel out right there, and I'm going to be left with joules. So keep track of your chickens, pigs, and cows. Literally keeping track of mine, because I got a little one now. I had to go out. Oh, going out in the cold snow, of course, trying to keep it alive. The mother's just a witch. She is. She's just a witch. She'll whack at me. Oh, she's just a witch. Okay. We gotta multiply this out. What do we get here? Ooh, two sig figs, 79,000? 79,000 joules? Yes. I think it's 79,000 joules, right? Please write down all your chickens, pigs, and cow units. Okay, next example. Page 262, number 9. It's from the book here. We had 344 gram sample of iron, 18.2 degrees Celsius. The sample absorbs 2.25 kilojoules. I don't want that in kilojoules. I want that in joules. How many joules? 2250 joules. So I want to identify for this one. Let's see what we've got here. So I'm going to identify everything over here. We've got 2250 joules is my heat. My mass, 344 grams. T initial is 18.2. You find what I'm looking for. And the specific heat of iron. Specific heat of iron doesn't give us there. Hopefully it's in the previous page. 0.449. All of my chickens, pigs, and cows, I'm going to write down with this. Joules over grams times degrees Celsius. So 0.449 joules per gram degrees Celsius. Okay, so we know we have Q is equal to MC delta T. the easiest thing to do is going to be to calculate our temperature change. Because we want to know what the final temperature is, right? So let's solve this. Let's solve this for our temperature change. So if we solve this for our temperature change, we're going to have Q divided by MC would be our temperature change. I should make that C bigger. If I'm dividing both sides by mass and both sides by specific heat, right? So then I'm going to sneak it in right here. 2250 joules divided by 344 grams. And my specific heat is 0.449 joules per gram. Oh, I got a little bit ugly here. A little ugly there. Not happy with that. I should end up out of here, out of degrees Celsius out of this, correct? So my other chickens, pigs, and cows are going to cancel out. In this case, joules, joules, grams, grams, right? Joules, joules, grams, grams. And my temperature change is my change, I believe, is 14.6 degrees Celsius. Anybody 14.6? 14.6. Okay. So my temperature change is 14.6. That should be T final minus T initial. So I'm going to have 14.6 degrees Celsius plus T initial is my T final. And my T initial is 18.2. So I am finally going to get 32.8. So Q is equal to MC delta T. All right, let's go to the next level with that. So I've got a good question here. I've got a good diagram with it. I've modified this and put text boxes over this. So this perfectly matches the problem for the book. Okay. So here's what we've got. In an experiment like that in the figure shown, 88.5 grams of iron. 88.5 grams of iron. At an initial temperature of 78.8. I'm going to put this as mass Fe. It's placed in a beaker containing 244 grams of water. So my mass of water in here (244 grams). The water is at 18.8. This is my T initial of my water. When thermal equilibrium is reached, what is the final temperature? So obviously, if you immerse this in here, this hot iron is going to cool down. Or more specifically, this hot iron is going to lose heat energy. This colder water is going to gain heat energy, correct? But the final temperature is going to be the same eventually over time. So I have a kind of a trick to do this. It's a lot less confusing, I think. We are going to use conservation of energy. I'm going to make 2 columns here. We know that the heat lost has to equal the heat gained. Conservation of energy, conservation of heat. Heat lost has to equal heat gain. Which one is losing heat? Which one is going to lose heat energy? We know the iron's going to lose heat energy, correct? We know that the water is going to gain energy. Right? Here's what we know. Our mass of our iron is 88.5 grams. Our initial temperature of our iron is 78.8. My specific heat of my iron is 0.449. My mass of my water is 244 grams. And my water initial temperature is 18.8. And my specific heat of water and then my final temperature is going to be the same for both, right? My final temperature is going to be the same for both. So I'll just say that T final of the iron equals T final of the H2O. Let's just call this T final, huh? That's what we got to solve for. We are looking for our final temperature. So let's do that right here. We're going to go Q lost equals Q gained. My Q is MC delta T, right? My heat energy, mass times specific heat times chamber temperature. So my Q lost again by my iron here. Is going to be my mass of my iron, specific heat of my iron, change in temperature of my iron equals mass of water, specific heat of water, okay, sometimes you can solve for one of these, and this time we're going to put our numbers in. But I've got to show you a trick that works. Otherwise, your book, I don't know. I think it does it a crazy way. I'm going to simplify this. I always want to do Q lost equals Q gain. Always, always, always. It's just that much. It's easier. All right, I'm going to start plugging this in, but we're going to do a little, don't get ahead of me now. So we've got 88.5 grams of iron. My specific heat of iron, 0.449. Now I'm going to take a time out right there. The trick to this, to do Q loss equals Q gain then, is to make your temperature change quantity a positive value. So it's not always going to be T final minus T initial. I might go T initial minus T final. Just so that that change in temperature is positive. So let's look at this. Now, is my iron, which starts out at 78.8, is T final going to be higher or lower than that? It's going to be lower than that, right? It's cold in cold water. This is going to decrease. So in order to make this temperature change positive, I'm going to go 78.8 degrees Celsius minus T final. It's going to cool down, correct? So I don't want to go T final minus 78.8. That would produce a negative in there. We know it's going to cool down. All right. So I'm going actually T initial minus T final. On this side, let's see how this works out. My mass of my water is 244 grams. My specific heat of water, 4.184 joules per gram degrees Celsius. And let's talk temperature change there. Is T final going to be higher than my initial temperature of the water? It is, right? That water is going to get warmer if it starts out at 18.8 and you're putting 78.8 degree metal in it. So in this case, in order to make this positive, this is going to be T final minus 18.8. Again, these are positive, right? This is going to be a positive number here. This is going to be a positive number here. Yes? Well, I'm going to get rid of chickens, pigs, and cows a little bit here and try to crank this through. I know at this point, I'm going to turn my microphone off. If you say, if you say I said this, I'm gonna lie and say I didn't. I know all of my units are in grams, they're in joules, they're in Celsius. I'm gonna crank my numbers now without the units. I didn't say that. I'll deny. I'm gonna crank this rest of the way without the units. It hurts to say. Okay, so we gotta go this times this, and then we gotta distribute this through, correct? We're just down to algebra now, correct? Just move on, or should we finish this pig? Let's get this thing done, huh? Okay. So 88.5 times 0.449. This would be 39 point, or multiple 7 times 78.8 minus T final. And over here, we're gonna have 244 times 4.184 is gonna be 10, 3 sig figs, 20 is fine, times T final minus 18.8. So now we're going to distribute this through. Yes, both of these are going to get distributed through. So we're going to end up with 39.7 times 78.8. This is 3130 minus 39.7 T final equals 1020 T final minus minus 19,200. I would just keep all my numbers in my calculator as I'm going, but I'm kind of doing sig figs as I go. Okay. What am I going to do? I'm going to add 39.7 T final to both sides. So essentially, I'm going to move this across the equal sign and make it positive. I'm going to move this across to the left and make it positive. Change the signs if you cross the equal sign. Cheers, math. Where are those math teachers? Show them how to do real math here. So we're going to end up with 3130 plus 19,200 equals 1020 T final plus 39.7 T final. So we end up with 22,330 equals 1059.7 T final. 1059.7 T final, yes. So if we divide that out, divide both sides, obviously, by 1059.7, we end up with 21.1 equals T5. think that's right. I screwed it up one time, had it wrong, but I think that's right. Okay, again, when you do these, just keep the temperature changes in the temperature change quantity here positive. So this one's actually T initial minus T final because I know my hot iron is going to be less of a temperature. I know here that my final temperature is going to be greater than 18.8 because this is going to go up. So keep your temperature change quantities positive. Okay. So we'll do this one, then we'll have some owl examples here again. We're going to skip to 5-6. It makes no sense. The order of this makes no sense. So I think that was, we just did 5-2. Specific heat, I think it's 5-2. We're going to 5-6. It just makes so much more sense to go to, you're talking about specific heat, we should go to 5-6 and then we're going to come back. Okay. So here's what we've got. We've got this device, which is a calorimeter. Now, I don't know if I drew this out. Did I draw out how we do calories of food? Food calories? Yes, no. Food calories? No. So food calories are basically, it's done like this. So it's called a bomb calorimeter because it's basically a pipe bomb. You take this metal and it's threaded here and it is thick. It is about this thick. It would blow up as a pipe bomb. It would be nasty. So we want to figure out how many calories are in our hot dog. We're going to put our hot dog in here. We're going to take that hot dog and we fill this chamber up with oxygen, full of oxygen. We bring an input wire in and we need to ignite our hot dog. And if it has oxygen in there, it's going to burn up, yes? When this burns up, of course, it's going to create heat. What is that heat going to do? It's going to heat this metal pipe bomb up, but this metal pipe bomb is in a tank of water. So we're going to put a stirrer in here. We're going to stir this water up and we're going to keep track of the temperature. If this is in here like this, both of these would start out at the same temperature if they're just sitting in there, correct? We're going to ignite our hot dog. That hot dog is going to create heat in there. It's going to heat the bomb calorimeter up itself, and it's going to heat the water up, correct? And based upon how much the temperature goes up, we know how many calories are in our hot dog. What produces a lot of calories? Oils, right? Oils, something that has lots of oils. You know, if you take a peanut and stab it with a pin and light it up, it'll burn for about a minute. Because you got peanut oil in that peanut. You get a lot of heat out of peanuts. So you get a lot of calories out of them, right? A lot of calories. Okay. So this right here is kind of a similar setup. A 455 gram chunk of metal is heated to 99.2. We just put that in boiling water. That heated up. It's dropped into a 52 gram aluminum calorimeter. So that bomb I explained before is a piece of aluminum. It's an aluminum cup. So the aluminum cup itself is going to absorb heat. That contains water. So similar to our hot dog heating scenario, this chunk of metal is going to heat up the aluminum cup and the water both. The initial temperature of the cup and water is 10. The equilibrium temperature is 21. It says find the specific heat of the metal. Whoa, doozy. We have 3 things going on here. We're going to make 3 columns. We've got our metal. We've got our water. And we've got our aluminum cup. There's 3 things that heat is moving here. So let's figure out what we've got here. I've got my mass of metal. I could put MM. I'm going to put MX. My mass of metal, 455 grams. Let's go across. My mass of water, 112 grams. And my mass of my aluminum cup is 52 grams. Now, T initial, T final. Okay. T initial of my metal is 99.2. My water starts out at 10. And my cup also starts out at 10. My T final. They all end up at the same temperature. I'm looking for my specific heat of my metal here. My specific heat of the water, 4.184. My specific heat of my aluminum is 0.897. Okay. So we know that Q lost equals Q gain. What's going to lose heat is my metal, right? It starts out at 99.2. What's going to gain heat is the water and my cup both, right? They're together. They're going to gain heat together. So the heat lost by the metal has got to equal the heat gained by the water plus the cup. So my mass of my metal, again, we're going Q. This is MC delta T. For all these, right? What are we trying to find here again? What are we trying to find? This. We're trying to find the specific heat of our metal. So let's start putting our numbers in here. I'm going to move over here, 455 grams times my specific heat. My temperature change is 99.2 minus 21.1. My temperature change is 78.1. My mass of water is 112 grams. My specific heat of water, 4.184. And my temperature change, my mass of aluminum, specific heat, so we can multiply these two numbers here and we don't see it. We can get the right side. So the right side, now sure. $57.19 joules. All my chickens, pigs, and cows are accounted for. Right, my grams are going to cancel out here. And my degrees Celsius, grams, degrees Celsius. 59.7 there. And I could divide by 455 grams and 78.1 degrees Celsius. Look at what happens. All the chickens, pigs, and cows come out perfectly, right? If we're looking for specific heat, we should end up with joules over grams degrees Celsius. And we end up with a specific heat of it's 0.161. must have showed you this last time, I think. Backside of your periodic table, bottom left has specific heat. Okay. Now, let's set up the next one because it relates directly to owl question. In fact, I've got an ugly owl right here. You're going to reuse, you would reuse this aluminum cup over and over and over. So it doesn't do any good to keep using the mass. The mass is never going to change of the cup. The mass of the metal you might put in it, the mass of your hot dog might be the different. Your bomb calorimeter mass is not going to change. So what they do is they roll the mass in and they call it a calorimeter constant. Now look at the calorimeter constant. It's 1.42 joules per degree Celsius without the mass. So the mass is built into this value. So here is an example where they just use what's called a calorimeter constant, and OWL does it, the textbook does this. So we've got 50 grams of lead, 0.15 joules per, so this sample up here looks like it matches lead, huh? 99 degrees is put into 75 grams of water at 4.25 degrees Celsius. Inside of a coffee cup calorimeter as shown to the right. Something like this, perhaps. The heat capacity of the calorimeter, sometimes referred to as the calorimeter constant, was determined by a separate experiment to be 1.42 joules per degree Celsius. What is the final temperature? Whoa. Final temperature. Whew. We've got 3 things to keep track of here again. We have the lead, we have the water, and we have the cup. 3 things to keep track of. My mass of lead being 50 grams. My mass of water, 75 grams. Ended up messing up my columns here. My mass of cup, not applicable, it's built in. My specific heat of lead, 0.159. Water, 4.184. And my cup, joules per degree Celsius. Missed it. Yeah. My initial temperature here of the lead is 99.0. My initial temperature of my water is 4.25. And my initial temperature of my cup is 4.25. We're looking for T final of all of these, right? T final. So what's going to lose heat? My lead's going to lose heat. It's at 99, correct? Both of these are going to gain heat, my water and my cup, both. But at the end, all three are going to be at the same temperature, correct? All three are going to be at the same temperature. So Q lost by my lead here, correct? It's going to be equal to Q gain, which is going to be the water plus the cup. So I set that up down here. So heat lost here by the lead is going to equal the heat gained by the water plus heat gained by the calorimeter. So obviously this should be my mass of lead, specific heat of lead, change in temperature of my lead. Now notice I type this first in. This is going to end up being positive, right? Because I know that's going to go down in temperature. Then I have my mass of water, specific heat of water. I know that the temperature of the water at the final temperature is going to be more than 4.25. Again, this is going to be positive, and this is going to be positive. So make your temperature change quantities positive. Okay, so we're gonna crank this thing out next time we meet, but hold on now, and then we've got this. So let me look at this quiz here. You should be able to try 1 through 7 on this. 1 through 7, yeah, 1 through 7. Oh, and 10. 1 through 7 and 10. You should be able to do 1 through 7 and 10. Sorry. 1 through 7 and 10. So today's Thursday, right? All right, so let's see everybody Tuesday, where maybe it's gonna be warmer, I don't know. No, I hope so.